A sewer diver is 30 feet underground when his oxygen monitor starts dropping, and in total darkness, he has no way to see what's changing around him. In this environment, breathing is not guaranteed, and what keeps him alive is a system most people never knew existed. The air can turn against you. The alarm does not echo loudly. It cuts through the helmet in a sharp, repetitive tone, oxygen level dropping. There is no horizon underground, no sky, no natural light. Only suspended particles drifting through a narrow beam and the constant sound of moving water. The diver freezes for half a second, not from fear but from calculation. Air is something most people never question. It surrounds them. It fills their lungs without permission, without effort. But down here, air is unstable. Oxygen can be displaced. Toxic gases can accumulate. Pockets of lethal concentration can shift without warning. And if levels continue to fall, the human body does not collapse dramatically. It degrades quietly. First, reaction time slows. Then coordination weakens. Then judgment fades. By the time confusion is noticeable, it may already be too late. In this environment, survival is not about swimming skill. It is about system design, and the system must work perfectly. What a sewer diver really does. Most people imagine sewer systems as empty tunnels. They are not. They are active, dynamic environments carrying wastewater constantly. Flow rates shift depending on usage above ground. Mechanical gates open and close automatically. Sediment accumulates unpredictably. Corrosion weakens surfaces over time. Remote tools can inspect certain sections. Machines can remove simple blockages. But there are moments when something irregular happens. A structural collapse. A mechanical obstruction wedged in an angle no machine can reach. A buildup that has fused into hardened mass. When that happens, a human becomes the final solution. A sewer diver enters confined infrastructure that was never designed for comfort, visibility, or stable air composition. This job exists because cities cannot afford failure underground. If wastewater stops moving, pressure builds. If pressure builds, overflow occurs. If overflow occurs, streets flood and public health is threatened. Therefore, the diver is not descending for exploration. He is descending to restore continuity, but continuity underground requires entering an environment where breathing cannot be assumed. The atmosphere is the real threat. Water is dangerous, but water is visible. Air is invisible. Inside confined underground systems, decomposition produces hydrogen sulfide, organic waste releases methane, oxygen levels fluctuate depending on ventilation and biological activity. Oxygen does not need to disappear completely to become dangerous. Below normal atmospheric concentration, the body compensates by increasing breathing rate. But increased breathing accelerates fatigue. If oxygen drops further, coordination begins to degrade. Fine motor control suffers. Decision-making slows. Spatial awareness weakens. And spatial awareness is everything in total darkness. Hydrogen sulfide presents a different hazard. At certain concentrations, it irritates the respiratory system. At higher levels, it can disrupt neurological function rapidly. Methane introduces another layer, flammability in confined space. Therefore, the underground atmosphere is not static. It is reactive. It shifts as sediment is disturbed. It shifts as flow changes. It shifts as trapped pockets are released. That is why the first layer of survival is not strength, it is detection. Gas monitors continuously analyze oxygen concentration and toxic gas presence. But detection does not prevent danger. It only reveals it. Layered survival systems. Survival underground is built on redundancy. No single device keeps a diver alive. Breathing systems are selected based on environment and expected duration. In some operations, air is supplied from the surface through reinforced hoses. In others, the diver carries a self-contained breathing apparatus. Each option has advantages. Surface supply allows longer operational time, but it creates dependency on hose integrity. Self-contained systems offer mobility, but they limit time based on stored air capacity. Therefore, operational planning determines which risk is more manageable. The diver is always tethered. The tether is not symbolic. It provides orientation when visibility collapses. It allows physical extraction if mobility fails. It carries communication lines when radio signals cannot penetrate dense infrastructure, but the tether can snag. It can wrap around protrusions. It can tighten if the diver changes direction abruptly. Therefore, tether awareness becomes instinctive. The diver must know the position of the line at all times, even when he cannot see it. Above ground, the support team monitors everything: air composition, communication integrity, elapsed time. The diver is alone physically, but operationally, he is never alone. Movement in total darkness. Darkness underground is not absence of light, it is absorption of light. Suspended particles scatter beams. Sediment clouds visibility instantly when disturbed. Often, the diver works in conditions where visual range is measured in inches. Therefore, movement is tactile. Walls are traced by hand. Structural changes are memorized by touch. Flow pressure is measured against the body. The diver constructs a mental map in real time. But mental maps can degrade under stress. If gas levels fluctuate, breathing rate increases. If breathing rate increases, oxygen consumption accelerates. If oxygen consumption accelerates, available time narrows. Therefore, pacing is deliberate. Rushing increases sediment disturbance. Disturbed sediment reduces visibility. Reduced visibility increases disorientation, and disorientation wastes time. Time is the only resource that cannot be extended underground. When the system fails. The most critical moments are not dramatic. They are subtle. A regulator stiffens slightly. Breathing resistance increases. A monitor reading drifts downward. Panic is the natural human reaction. But panic consumes oxygen faster. Therefore, training overrides instinct. Confirm reading. Switch to backup supply if necessary. Communicate status. Initiate withdrawal sequence. Withdrawal is often more dangerous than entry. The path may be altered. Debris may have shifted. Sediment may have reduced visibility to zero. But the tether remains. Follow the tether. Always follow the tether. If communication fails entirely, pre-established tension signals transmit status. Surface teams are trained to interpret silence. If no response is received within protocol limits, retrieval begins immediately. There is no waiting for confirmation when air is uncertain. The psychological edge. Working in complete darkness changes perception. The absence of visual reference distorts time. Sound echoes unpredictably. Isolation amplifies minor sensations. Therefore, mental conditioning is as critical as technical training. Divers rehearse confined scenarios repeatedly. They practice breathing control under simulated stress. They learn to separate imagination from data, because imagination consumes energy, and energy underground must be conserved. Confidence in procedure replaces reliance on emotion. Emotion fluctuates. Procedure does not. Why humans are still needed. Technology has advanced. Remote inspection units enter narrow spaces. Sensors map gas distribution. Robotic tools remove certain obstructions. But sewer systems are irregular, built across decades, modified repeatedly, documented imperfectly. Machines operate well in predictable geometry. But unpredictable geometry still requires human adaptation. A human can interpret resistance through touch, adjust angle dynamically, evaluate stability instantly. Therefore, the profession persists. Not because danger is ignored, but because human adaptability remains unmatched in chaotic, confined environments. The final structure. The most dangerous job underground is not sustained by bravery. It is sustained by layered engineering, detection before exposure, redundancy before entry, discipline before instinct, withdrawal before pride. Survival here is procedural. The diver does not descend because he trusts the air. He descends because he trusts the system built around him. Above ground, cities function normally. Water flows, streets remain dry, infrastructure remains invisible. But beneath that stability is a network that occasionally demands human presence in total darkness, where breathing is monitored, not assumed, where time is calculated, not wasted, where survival depends on invisible structure more than visible strength. And that is how this job remains possible, even where oxygen isn't guaranteed. The limits of the human body. The underground environment does not need to collapse to become lethal. It only needs to shift slightly beyond the range the human body can tolerate. Oxygen is not just fuel for breathing, it regulates cognition, muscle control, balance, decision-making speed. When levels decline gradually, the body attempts compensation. Heart rate increases, breathing becomes deeper, but compensation has limits. In confined spaces, even minor miscalculations amplify risk. If oxygen concentration drops below safe range, judgment deteriorates before strength does. That is what makes it dangerous. The diver may still feel physically capable, while cognitive clarity is already compromised. Therefore, reliance on subjective feeling is forbidden. Every decision underground is instrument-based. Gas monitors are positioned strategically to capture air composition continuously, but readings are only useful if interpreted correctly. A slight downward trend may not trigger alarm immediately, yet trained teams recognize patterns. They evaluate trajectory, not just current value. Trend analysis becomes survival analysis. If readings fluctuate repeatedly in short intervals, it may indicate unstable gas pockets. If oxygen oscillates, ventilation in that sector may be inconsistent. Therefore, the environment is assessed dynamically, not statically. The diver's role is not just physical labor, it is environmental interpretation under pressure. Confined space dynamics. Confined spaces behave differently than open environments. Air does not circulate freely. Heavier gases settle into low points. Lighter gases accumulate near ceilings. Temperature gradients influence gas layering. Flow turbulence can mix layers unpredictably. This means safe air at one height may not be safe a few feet lower. Therefore, vertical positioning matters. When a diver descends into a deeper shaft, air composition can change rapidly. That is why atmospheric testing occurs at multiple depths before full entry. Water flow also behaves unpredictably in confined geometry. Narrow channels increase velocity. Sudden expansions reduce it. Obstructions redirect force. A diver working near a restriction may encounter stronger currents than anticipated. Current strength is not only about movement difficulty, it influences stability. It pulls against equipment, it shifts debris, it increases metabolic demand. Increased metabolic demand increases oxygen consumption, and oxygen underground is finite. Therefore, energy conservation is not optional. Every movement is calculated, every action is intentional. The entry protocol. Before a descent begins, the system is stabilized as much as possible. Upstream flow may be temporarily reduced when feasible. Mechanical gates are secured. Surface access points are reinforced. Lighting at entry shafts is optimized. Then comes the sequence: air check, secondary air confirmation, gas monitor calibration, tether integrity verification, communication test, emergency retrieval rehearsal. No step is symbolic. Each step eliminates uncertainty. Because underground, uncertainty multiplies. Once entry begins, the diver transitions from open air into confined atmosphere gradually. Gas levels are monitored continuously during descent. If instability is detected early, retreat is immediate. But once committed deeper into the system, retreat takes longer. That is why entry decisions are conservative. You do not enter hoping conditions will remain stable. You enter only when conditions are verified stable enough to complete the task within controlled limits. Task execution. Under constraint. Clearing an obstruction underground is rarely straightforward. Debris accumulates in irregular shapes. Organic matter binds with inorganic material. Hardened buildup resists removal. Tools must be selected carefully. Mechanical cutters introduce vibration. Vibration destabilizes sediment. Sediment reduces visibility. Reduced visibility increases reliance on touch. Therefore, tool choice balances efficiency with environmental stability. Sometimes manual removal is safer than powered equipment. Slower, but controlled. The diver works within limited mobility. Arm extension is constrained by tunnel diameter. Body rotation is restricted by tether and equipment bulk. Fine motor tasks require patience. Meanwhile, the clock runs silently. Air supply duration is calculated before entry. Every delay shortens operational window. If unexpected resistance is encountered, a decision must be made. Continue and risk extended exposure, or withdraw and return later with adjusted strategy. Withdrawal is often the disciplined choice. Pride has no place underground. When visibility collapses, there are moments when sediment becomes so disturbed that visibility drops to zero. Not low, zero. The diver's light reflects back immediately from suspended particles. In that condition, sight becomes irrelevant. Orientation relies entirely on tactile reference. The tether becomes a directional guide. Wall curvature becomes a compass. Water pressure becomes a clue. Panic in zero visibility is common in untrained individuals, because the brain depends heavily on visual input for stability. Remove visual input, and disorientation increases rapidly. Therefore, divers train in simulated blackout conditions repeatedly before ever entering real systems. They practice stopping movement, stabilizing breathing, recentering orientation using touch alone. The difference between trained response and panic response is measured in oxygen consumption. And oxygen consumption determines survival margin. The extraction window. Every operation has a defined extraction threshold. It is not based on exhaustion, it is based on safety margin. Air supply is never consumed fully. A reserve is mandatory. If environmental readings fluctuate unexpectedly, that reserve provides time for controlled exit. But if a regulator malfunctions or tether entangles during withdrawal, reserve air becomes critical. Entanglement is a real hazard. Debris fields can shift during task execution. A loop of tether may slide into a crevice. Equipment edges can catch. If the diver feels unexpected tension, the correct response is not forceful pulling. Force can tighten entrapment. Instead, controlled backtracking is initiated. Identify obstruction point. Relieve pressure gradually. Maintain calm breathing. Surface teams monitor line tension and can assist by adjusting slack. Coordination between diver and surface is continuous. Without that coordination, extraction becomes exponentially harder. Incident analysis and system evolution. In this profession, safety improves through systematic review. When near misses occur, they are documented in detail. What environmental conditions were present? What readings were observed? What response time occurred? Was there delay in decision-making? Did equipment perform as expected? This analysis feeds procedural refinement. Checklists expand. Redundancy increases. Exposure limits adjust. The job remains dangerous, but it becomes more structured over time, because survival underground is not static. It evolves. Technology versus human adaptability. Robotic systems continue to improve. Remote-operated units inspect confined pipes. Automated cutting tools remove certain obstructions. Gas mapping sensors provide real-time atmospheric distribution data. These tools reduce frequency of human descent, but they do not eliminate it. Irregular geometry still defeats rigid machines. Unexpected structural weakness requires judgment. Unstable debris requires adaptive manipulation. Human adaptability remains unmatched in complex confined spaces. Technology supports, humans execute. The invisible dependency. Above ground, life continues uninterrupted. Water flows, facilities operate, infrastructure appears seamless. But that seamless function depends on systems maintained in darkness. Few people consider the network beneath streets. Fewer consider the individuals who enter it. Yet without intervention, failure compounds quickly. Overflow escalates, pressure builds, structural damage spreads. Therefore, the sewer diver operates at the intersection of engineering and biology. Engineering manages structure, biology manages tolerance. The diver stands between system failure and systemic breakdown. The final reality. The most dangerous job underground is not defined by dramatic moments. It is defined by controlled exposure to invisible variables. Air that can change without warning. Space that restricts movement. Water that shifts force. Darkness that removes orientation. Survival is achieved not by eliminating danger, but by anticipating it, layering systems against it, training against instinct, designing withdrawal thresholds before crisis occurs. Where oxygen isn't guaranteed, complacency is fatal, but procedure is powerful. And that procedure is what allows a human being to descend into total darkness, work with precision, and return safely to air most people never question. That is how the system holds. That is how the job continues. And that is why, even in the most hostile underground environment, survival remains possible.